today I'm going to be talking about B3. I'm going to do a little bit of salesmanship first before we get into the topic. I'm basically trying to cram 5 different talks into 45 minutes. So luckily you won't stay here for 5 hours, but I might skip around. Don't hesitate to ask a question or stop me, or if I use some jargon or term that's not well understood, please ask. I don't want to lose you. This is our lab. We're down in Mountain View. There's about 70 researchers. This is from 2 years ago. I'm in there somewhere, but this is the back of the building. We do a variety of things. Microsoft Research is about 850 researchers worldwide. That's about 1% of the company. We in the Bay Area have about 70 researchers. We look at a variety of different things, from practical things like computer architecture, systems, to theory. And so there's just a wide variety of things we do. I work with a lot of famous people in my industry, which is amazing. And we do a lot of industrial and academic collaborations, and the B3 is an example of that collaboration with academia. Lots of awards. If you can name the high award, there's someone in our lab that has it. And we have done a lot of tech transfer. So our first goal is to actually advance the state of the art. That's actually doing research. The second goal for our lab is to actually take that research and transfer it to products within Microsoft. These are the technical areas, algorithms and theory. That's the theory side, as you can imagine. Lots of math, lots of very smart people. Distributed systems, lots of computers everywhere. How do they work together? How do you find the problem of that one computer that breaks everything? We do security and privacy, software tools. I fit into the systems architecture and computer architecture, web search, and data mining. So think of your normal search engines, AdSense, how you actually pay for ads, those types of things. That's what's down there. So let's actually dive into the purpose of my talk. I'm going to talk about Silly Putty. I'm going to go through some jargon. I'm going to introduce you to the B3. It's a FPGA platform. We're going to hopefully discuss the reconfigurable computing space, and I'm going to try to motivate why the B3 is useful using 3 different areas of application. So I'm going to go through computer architecture. I'm going to talk about systems architecture, application or algorithm acceleration, and I'm going to try to wrap things up and give you a big picture view of why this is significant. And hopefully you'll agree that Silly Putty and B3 are very similar. So let's start with Silly Putty. It was created in a research lab back in the 40s. It was a very long time ago. It's a silicon-based polymer, which is very interesting. They spent about 10 years trying to find a practical use for this material, and they actually couldn't. It has properties both of a solid and a liquid, and we'll go into those. So basically, if you bounce it, if you throw it hard, it bounces like a solid. If you do something abrupt, it has solid properties. If you do something slow or purposeful, it has more liquid properties. So you can stretch it. If you pull it really fast, it snaps. I don't know how many newspapers still use an oil-based printing material, but you could take the Silly Putty, flatten it out, put it on the newspaper, and then transfer that image somewhere else. And so if you do this with politicians, you can deform the image and then transfer that deformed image somewhere. So that was fun for me as a kid. In the 50s, it started out as a toy. It sold more than crayons, which is interesting when it first debuted. And finally, it's traveled to space. So astronauts have used Silly Putty to stick tools and keep them in place. So it has a long and illustrious career. Who knew? Some of the jargon I'm going to talk about today, the FPGAs, those are field programmable gate arrays. Basically, they're various kinds of building blocks that make up an FPGA. And there's basically 2 types of networks. There's the sea of resources network. So this is the DSPs, the processors, memory arrays, Ethernet, these hard macros that do special purpose functions. And then below that, there's a control network that actually connects them up. So you write a program that controls the control network, and that tells you how to hook your components up. There's a bunch of high-speed I/O, which we use for a variety of things. And then what most people associate with FPGAs are the lookup tables. These are basically arrays that can hold any value you want. And at this point in time, we're using 6 inputs. So 2 to the 6 is 64. So any 6-input function that's a Boolean logic you can represent by just writing in the values. If I have these inputs, I get this output. And it's a very straight process of a lookup table or array. We put all this together with a printed circuit board, or PCB, and that's basically multiple layers of fiberglass or some other fancier material. And in between those layers are actually wires that hook points from one chip to the other. And so that gives you the connectivity. And that's the kind of the fancy things that we use there. In terms of reconfigurable hardware, this is the B3. It's a picture of it, lots of words. Basically, about 3 years ago, Dave Patterson came to Chuck Thacker and said, hey, give me $500,000. I want to build this B3 platform for the RAMP consortium. And RAMP is the research accelerator for multiple processors. And Chuck, being who Chuck was, said, no, that's a bad use of money and a bad use of grad students. We'll build it for you. And so what we did is we sat down and came up with a spec, and we came up with a Berkeley Emulation Engine 3. There's 4 FPGAs on it, about 64 gigabytes of memory, so it's a lot of memory. It's unlike other boards. There are, of the 4 FPGAs, each FPGA has 2 DRAM channels. Each channel can hold 2 DIMMs, so it's a normal server memory, nothing fancy. We're trying to utilize PC economics, so the power supply, the DRAM, all that stuff comes from the PC world, so it's relatively cheap. There's a ring interconnect, plenty of IOs. And again, what we were looking at was the architecture space, the mini-core architecture research. There's some system stuff, and I'll talk about the Flash research platform, and also algorithm acceleration. So as a block diagram, this is kind of what the whole system looks like. We have these user FPGAs. There's the ring that connects them together. This is kind of a vestige of DSPs. If you're doing any type of digital signal processing, there's this idea of producer-consumer applications where you do some computation here and forward it on to the next one, and that ring allows you to do that pretty efficiently. The DRAM, the 2 channels, the CX4 are 10 gigabit Ethernet ports, so you can actually do 10 gigabit Ethernet if you want. QSH is a fancy connector. It's all it is. It's nothing earth-shattering. That's all that is. And then there's PCI Express, which allows you to connect each FPGA to a host PC. So think of your graphics card. Those all plug in as a PCI Express device. You can actually now have an FPGA with 16 gigs of memory hooked up to your processor and offload computation there. And that's kind of some of the models we have for how this all works. All right. I've kind of gone through that at a very high level. Hopefully there are no questions. Everyone's following me? Okay, so we have this hardware. Now what the hell do you do with it? That's like the big question. And that's the problem, because the hardware alone is just a heat sink. It's a good egg cooker or something. You actually have to program it with something and then actually use it, right? So that's kind of the long and hard part of that. So the primary focus was computer architecture, so I'm going to dive into what we're doing at Microsoft. And as you can imagine, it's called B3, so we had to come up with a name that was similar to, or at least connotes B. So we came up with Beehive. And the interesting thing about Beehive, it's a multiprocessor system. They use a ring to communicate, and I'll show you a picture of that later. But we've targeted it not only for the B3, which is a bigger system, but you can also use it for this academic system out of Xilinx. It's the XUP board, and depending on where you are, in the academic realm, they cost as much as $750. Some people get them for free. Just depends on who you know in Xilinx, and who you know gets you a long way. That's just life in general. It has a smaller FPGA. So the interesting thing about this board is the FPGA that we used to prototype the B3 was that same one, this LX110T. When we bought them, they were $2,000 a piece. And you can get a board for $750. So I'm a little disgruntled, but we won't take it much farther than that. There's lots of stuff on it. It's very similar to the B3, except it's just one FPGA. And so we map Beehive to this platform. And so the difference between it and the B3 is on a single FPGA, you can just put more stuff on the B3 FPGAs. And that's all. This is about 2/3 the size of a normal B3 FPGA. So what it is a multi-core RISC. The actual processor was developed in-house. It's a program. And you write a program to have your processor do add, subtract, multiply, all the things that a normal processor does. We write that in Verilog and then synthesize that down, and it maps to the FPGA components, and voila, you have a processor that does stuff. It runs at 100 megahertz, so I think 10 years ago that was fast. In late 90s, now not so fast. For the XUP board, there's 13 cores per FPGA, which is actually pretty good. And we're not even using all the resources. We kind of stop at 13 because as you add more to the system, it takes longer to push it through the tools process. So this takes about an hour to build. If you add more, it's kind of an exponential increase. It can take multiple hours or days, and so that's a bad thing. We have a C compiler, and the nice thing is it's a very small design, so it's very easy to change. So it's very easy to understand. There's a couple thousand lines of code. You can give to someone, and a couple weeks later, they can play with it, understand it, and make changes. So that's kind of the cool thing about this. And it's optimized for the FPGA fabric. So in terms of the software, we're using the same things you see in Linux, right? There's GCC, which is a compiler, and you can retarget GCC, the nice thing about it, to kind of any platform, which is cool. We have an assembler, AS, and if you're in Linux, LD for the linker. So these are the normal things that you see when you actually build software from C. And we do, well, it's not an old trick, but even now with Pixie you can do this, but we basically have a small kernel that is programmed into one of the cores, and it goes out and from a TFTP server fetches the program. So you can basically run anything you want on it within reason. I'm being a little bit exaggerating, but we use an old style TFTP bootloader to actually load programs in to Beehive. So that's kind of an interesting way to do that. This is the processor at a block diagram level. You have the ALU, which is the thing that actually does the computation. There's a register file. There's 32 registers, an instruction cache. And kind of the novel thing about this architecture is we're actually using queues to access memory, the data cache. And so that's a very different way of looking at things. So you put in an address in the address queue if you want to do a read, and later on the data comes from the read into the read queue, and then you get the data. So it's not the traditional way of thinking about caches or accessing memory from the data side. Similarly, you put an address in the data value for a write, and then that writes it to the data cache or the memory, depending on what's happening. So it's a kind of cute design, and this is very small. So what you get from this design is something that's totally visible, it's totally transparent. Anyone can look at the source code. It soon should be on the web. It's smaller than anything else that's out there, and so that means you can put a lot of them on the FPGA. So in terms of the overall system, this is kind of what you get. Core 0 is the memory controller. That's the interface to the DDR2. And then the cores are strung along on a ring. And then there's also the Ethernet controller, which is also on the ring. And so you communicate on this ring, sending messages, sending data, and doing what you'd like to do. In terms of a normal multiprocessor system, there's no memory coherence. So if Core 0 knows something, that doesn't mean that Core 1 knows it. That's kind of the coherence side of things. Normal processors today, if you think of your x86, use interrupts. There are no interrupts. They haven't been implemented. No memory protection. There's no MMU, memory management unit. No virtual memory. No kernel mode. If you think of protecting OS operations and user operations, there's usually different modes to do that, or rings. No memory bus or I/O bus. So you have the option of either implementing them yourself in hardware or doing them at a software level. So there's a trade-off that you can make there. So, but the nice thing is that they can be done. It's not a matter of it's not possible. So we went through this whole process. Chuck and Andrew and Tom came up with this whole design. They pushed it out. And one of the things they want to do is push it into the academic realm. How do you teach folks like yourself how to parallel program? What are the issues? What are the ways of playing with real hardware? Because sometimes it's hard to get access to complicated machines. Nowadays, with quad and bigger core machines, you can get access to some issues, but you can't see all the nasty details if you want. So this past winter, they did a short course at MIT. There were 14 students, 4 faculty members. Andrew was from MSR, from our lab. And basically, we gave them Beehive and said, hey, for the systems folks, so these are people that usually work at the OS level and higher, here's a multi-core system. Let's play with it and see what you think. And so in the interesting case, everyone was able to write bare metal multi-core programs. So when you think of an application or processor or the system, what I mean by bare metal is there's no operating system. So if I boot Linux or I boot Windows or whatever, that operating system runs applications. In this case, I'm actually running the application directly on the hardware. There's no OS services, so something a little bit different. Everyone was able to change the Verilog, so this is the hardware description. And so they said, I have an idea. I want to do this. So let's say I want to change the lock unit if I'm doing some type of concurrency programming. I'm going to change the hardware, I'm going to change the software, and then they're going to work together to make my program faster. And they were actually able to demonstrate this in a week. Everyone had fun. There was one dropout. And currently, we're looking for other schools that are interested in using this. So it might come to a school near you if your faculty is interested. So this is an interesting case of we're starting from the bottom. If I look at the whole stack, we have an architecture which is a hardware description. We're able to play with it and facilitate higher level research. And that's kind of the interesting thing. So we'll move on to higher level stack issues. All right. Any questions? Excellent. So system architecture. So this is OS, storage, networking, anything above the hardware that interacts with stuff. We're not really doing distributed systems, but we're going to focus on a single system in this case. And what we did was we had this problem. We would go to meetings that various flash manufacturers, NAND flash manufacturers, would come to you, and we'd ask them questions about their flash product. How does it fail? What are the operating modes? What are the information that's not talked about in the data sheets? And we really got no answers. And so this motivated us to create this flash research platform to explore issues with flash. So right now, many of you probably have iPods. There's hard drives called SSDs that are coming out that are flash-based. There's all these things that are coming out that change the way the computer thinks about storage, persistent storage. And so we, as a software company, I'll be Microsoft Broad, have to deal with issues like how do you defrag a SSD? There's all these issues with how flash works that isn't the same way as a disk. And so this platform is there to help us, as we build it, answer those questions. We wanted a large capacity, so we can do up to 0.5 terabyte in a B3 box. And that's using a single level cell, NAND flash. If we use other technology, we can actually go up to above about 2 terabytes. There are a variety of I/O options, the 10 gigabit Ethernet, the 1 gigabit, the PCI Express, to connect the B3 to a PC so you can have some type of communication. And this allows us to play at the hardware level, the software level, or both, depending on where you're comfortable. So I can make changes to the hardware, I can make changes to the software, or what have you. Now, we're doing this because flash is a lot different than a hard drive. You have to write it in order. You write it in the granularity of pages, which are on the order of 4 kilobytes. But you erase on the order of blocks, which usually is 64 to 128 pages. So there's a big asymmetry there. There's also an asymmetry on how fast writes are and how fast reads are. So there's all these little quirks that you have to play with. And in this picture kind of illustrates what that flash platform looks like for the research. You have your host PC like you do in most other things. There are input and output queues that allow you to communicate between the B3 and the PC. There's a data management unit which does the DMA, metadata, cache, all these different types of engines that you have to do to track and manipulate your data. And then there's a flash interface which actually does the writing and reading to the hardware. And if you were to open up a hard drive nowadays, you'll see that they also have a disk cache, a write buffer, and that's what the DRAM is for. So what we ended up doing, the B3 has these DDR2 slots, and we repurposed them for flash. And so we started out with Samsung devices. They're 4 gigabyte single level cell. Each cell holds 1 bit of data, as opposed to cells that hold 2 or 3 bits of data. We're basically taking that DDR2 interface, those wires, and because it's an FPGA, we can repurpose them to be whatever we want. So we say, okay, we'll just split that up into 8 individual channels, and the FPGA can individually talk to each one of these flash chips. And there are the 8 there. The CPLD is a programmable logic device. This basically does a voltage translation between the 1.8 volts that is physically given as signaling to the DDR2 slot and translates it into the 3.3 volts that these speak. So that's all it's doing is a pass-through device. And then JTAG allows us to program and actually observe the PLD. So that's kind of the additional component that we had to make for the B3 in order to actually do the flash research. If we look at the software side, there are 3 distinct steps. And we're in step 1. So we're starting this whole process. This is basically the hardware. So anything below this is the B3. Anything above that line is, think of your host PC. And what we ended up doing was we created a disk interface. So there's known drivers for file I/O that treats a file like a disk. And we were able to intercept from a user level application requests for the disks. Those go to this interface driver. We push those requests back up to a user level management software package. It does some stuff, and I'll get into that in a little bit. And then it connects to a communication driver and pushes that to the B3. We take this approach because if we use a user level management layer, we don't blue screen the computer. And device drivers are notorious for your blue screens in Windows. That's a whole different discussion that we can have. But this makes development much easier. If you did the development of the user level stuff here, you'd get a blue screen. You'd have to restart, unload the driver, all that stuff. But the goal is to actually make it more streamlined and push us this way. So in the second step, we're taking that user level management layer that's been debugged and works, pushing that into the driver interface, and getting rid of these hops, because those add a lot of overhead to the overall process. I have to transition from user mode to kernel mode and then back again, and that just adds a lot of latency. And we're trying to make it more like a Fusion I/O device. That's kind of the closest thing that you can think of. But in this case, we can push the functionality of the user level management layer. We can keep some of that in the user level application. We can put it in the interface driver, or we can put it in the FPGA. And then the third and final instantiation of this is actually making it more like what you'd think a SSD is, the solid-state drive. You have the flash translation layer in the FPGA, and then information that helps you in the interface driver and user level. But regardless of how you do that, you now have a system that people can play at whatever level they feel comfortable with and make changes to the system and see how that impacts the overall operation, either the operating system, the storage, what have you. All right. Looking at the actual management layer, what we're doing is we have all these different tasks that cooperate together and actually handle all the issues. So one of the problems with Flash is it actually will wear out, and you use ECC and error correcting code to make sure that the data you get back from it is correct. We implement 8-bit BCH, which is a type of ECC. That takes up one processor running at 2.4 gigahertz just to do that one task. I mean, that's pretty intense. So we definitely want to move that to the hardware because that's pretty crazy and done in software. It implements the log structure file. So as I mentioned before, Flash is written in order. It's a sequential process. And so when you modify a file, the Flash actually adds that modification to the end of the disk versus a regular hard drive, which actually writes in place. And so that log structure needs to be maintained, and pointers need to be maintained. And so that's what that does. If we were to write the same block and erase it over and over again, it would finally fail and wear out. So you'd have a weird distribution of failure modes, and that can cause a lot of problems, which I won't get into. But we have to do wear leveling. When I erase a file or make an update to a file, I have to garbage collect the old data. And so doing that is the garbage collection process. The FTL, this flash translation layer, allows you to map the logical address of the page for storage to some physical address. And so you have to do that assignment. And that's what page mapping does. And there's a bunch of other metadata that you have to keep track of. Yes? It depends on the manufacturer and what they tell you. So on SLC parts that we're talking about right now, you can think of a block having a lifetime of about 100,000 erase cycles. If you do some fancy things, you can extend that to 1 million. The nice thing about Flash is the bigger the disk, the better it is. But they're more expensive. If we go to the MLC technology, which basically I store 2 or more bits per cell, so I have 4 values instead of 1 or 2 values instead of 4 values instead of 2 in the 2-bit case, those cells and pages actually don't last as long. They're in the 2,000 range, or 1,000 to 10,000, depending on what you're doing. So for your iPod, it's great, right? Because you don't necessarily erase your music that much. For your disk, every time I put this thing to sleep, I write a lot of stuff. If I do that over and over again, I wear out the disk pretty rapidly. So it all depends. Just as a side note, MLC is targeted towards consumers, so that's you guys. SLC is targeted towards enterprise, so think of the data center or something like that. So, and there's different things you can do with the FTL to make it try to last longer. But if you get a flash drive, an SSD, bigger is better. It's unfortunately more expensive, but that's the process. Any other questions? All right. So what I'm showing here is us mounting the Flash Research Platform as a disk. It shows up. In this case, we just mounted it as S. You can mount and unmount. You can get properties of the disk, how big it is, how full it is, those types of things. Read, write, erase files. And we've done different stress tests to actually make sure that it works. So a first step, even though this is very slow, we can actually see it as a component in the system, which is kind of cool. Whether I use SLC or MLC flash DIMMs, that will tell me how much each DIMM can hold. And so I have anywhere from 8 gigabytes to 128 gigabytes per DIMM. And if I put 16 of those in a B3, I can get up to 2 terabytes. So that's kind of cool. I can do a lot with 2 terabytes. Cost-wise, not so cool. So there's a trade-off. And then we did a demo last year where we actually mapped the blocks and the operations of those blocks to an application and visualized it. So from that perspective, what you'll see is there's a line that corresponds to each page, and the green ones are valid pages. This color, which is a light green, I guess, is invalid pages. And then depending on what you're doing, we show which operation is currently happening. So if you were closer, the people in the front row can see this. We have a series of blocks that are actually being erased, and you can see the red. We're doing a lot of reads, and there are some sprinkled in greens showing the writes. So it was just a random test that allows you to visualize what you're actually doing to the flash and making sure that the overall management software was working. So that was kind of cool. At least I thought it was cool. All right. And this is just a B3 with some of those devices. So there's a lot of different ways, because it's an FPGA, to configure it. In this case, we're looking at this FPGA kind of being the control head node with DRAM to actually do the metadata management, the caching, that kind of stuff, and then using the ring interconnect, which is in the printed circuit board, to connect to flash DIMMs in other FPGAs. And so because we're using the ring in this case, the nearest neighbors are the top corner and this bottom corner. And so that would give you added functionality. This is nowhere near populated fully, because you could put 2 DIMMs per each channel and make it bigger, but this is just showing how you could expand it and use it in a pretty straightforward way. Going from a single FPGA instantiation to this is not that difficult. It's difficult, but it's easier than doing some other things. So that's kind of what the overall system looks like. And this is actually a prototype system because it's silver. The production ones are black. All right. So that's kind of a view into the system. So we've started out at the hardware level with the architecture. We've moved up in the system level, so OS, storage, that kind of stuff. And the next thing is applications, the things that you run normally on your desktop or whatever. We'll talk about 2 different application accelerators. The first is a SAT solver. So Boolean satisfiability just says, can I find assignments to these literals, so the variables. Let me step back. A variable is x1. The instantiation of that variable in a clause, so that's a clause, is a literal. So we have the literal x1 and the literal x1 bar, right? And so what we want to do is find out assignments to all these values that make that entire clause true. And that's all we're talking about. In this case, we have 3 literals per clause, so that's a 3-SAT problem. And this is the first known NP-complete problem. So if you've done discrete math or are going to take discrete math, you will learn about NP-complete if you haven't already. That just means the problem is really hard, and there's no known way to solve it in a very short amount of time. They have heuristics to try to approximate it, but there's a lot of work to be done. So if you're on the theory side, great problems to tackle there. The application for SAT is kind of everywhere. The nice thing about NP-complete problems is you can actually transform other NP-complete problems into this one and then solve it. So if you have heuristics for 3-SAT, let's say, and you have the other type of NP-complete problem, I can transform it into a 3-SAT problem and then use its solvers to find an answer. So verification and circuit design, so CAD stuff, that's a good example of stuff. Crypto attacks. If I'm trying to break your key and find out what your bank account number is on my HTTPS server, that's kind of stuff like that. And so the problem is if I can make SAT faster, I can make all these other things faster because it's a component in that application pipeline. So that's what we were trying to do. It's a pretty straightforward process. We're using a hybrid approach, so we're using hardware and software. The hardware in this case is the FPGA, and the software is the software running on your PC. And there's 3 main points of this application. There's the decision, pick a random variable and setting it to 1 or 0. there is the deduction. Once I've set that variable to 1 or 0, does that allow me to infer values of other variables in my clauses? And then there's some backtracking and conflict analysis. Sometimes I go down a path that's incorrect, so I have to backtrack and come back up. So when we look at the profiling of this application, about 10% of the time is spent here, right? And 90% of the time is spent there. So if I'm going to try to accelerate something, I'm going to try to accelerate something that we spend the most amount of our time in. That's just kind of how you do things. So that's what our target is. And just an example in this case is I'm going to set x1 to 0, right? That's a decision that I've made. I say x5 equals 0. What does that imply about x9? And to make this clause true, x9 has to be 1, right? Because that's the only thing it can be. If it was, or sorry, 0. If it was 1, it wouldn't work, right? So that allows me to go through that process. And this is very straightforward. I mean, that's all that's happening. And the interesting thing about this is probably for the last decade been the process that you do it. The research has happened in how you pick the variables and how you do conflict analysis and backtracking. So you can still do research on the software side, but this thing that hasn't changed, we'll put it in the hardware and hopefully get acceleration. And as I mentioned, keep this in your CPU. So that's the normal software stuff. And we map to in this case, a Vertex 5, the deduction process. So now you guys can all do SAT. Isn't that great? No? Okay, never mind. All right. So what did previous work do? In this case, they were trying to take those clauses, and because we have these FPGAs which allow you to map functions to them, so these clauses are functions, they would take that function and directly map it to the FPGA. And it's a very common sense thing to do. The problem is that you have to reprogram the FPGA for every new clause, so you can't reuse the FPGA substrate. For large FPGAs, we're talking hours or days. And the more you fill up the FPGA, the harder it is to actually do that. So what we've done is we've changed this from a logic problem to something that is better suited for the FPGA architecture. We're using the memory on the FPGA. We're using the logic and putting them close together to do computation and indexing at the same time. So what we've done is we transformed a logic problem into a memory indexing problem. I'm not going to go through the specifics of how that happens, but it's an interesting twist on how you can actually rethink a problem and map it to the FPGA as opposed to try to force the FPGA to do a particular thing. So it's just stepping back to take a new look. So within the FPGA, we have 5 different components. As you saw in the Flash research platform, there's a communication infrastructure. That's number 1. So how do we communicate between the CPU and the FPGA? There is the implication queue, which basically queues up our decisions. There are the learning engines, the inference and learning engines. These basically have an array of clauses in them, and each one is separate. So when I look at these clauses, and I have a literal, let's say A, I try to cluster as many clauses in this inference engine that only have one instance of A. And then when I come across another clause with another instance of A, I put it in a different engine. And so when I make that decision on A, basically I say A equals 0. And then all of these inference engines can see if they have A and then actually do that computation in parallel. So that's the parallelism that I actually get from the FPGA. Once I do that, I have to push that out, and there's basically a serialization process, and that's all this is doing. So I've gone from serial, parallel, serial, and then a serial lookup again. And so in this case, I need to see if I have an inference, A setting A to 1 makes B 0. That inference, I need to make sure that doesn't cause a conflict. And so that's what this global memory does. And in reality, what ends up happening in this process is I bring in all these decisions. They actually go into the conflict inference detection engine first because I have to do a global to local translation of the indices. I have to make sure that I haven't created a conflict. I push them into the implication queue, and then one by one I issue each decision, and then I let it percolate through. So even though this is numbered in a particular order, the way that it happens is slightly different. All right. So the process I've been talking about within the FPGA is called the Boolean constraint propagation problem. In the FPGA, we can do that 15 to 16 times faster than software. And this is just data showing that. These are various applications that we're using to drive the research. But that's just a small part, right? There's still the end-to-end time And that's something that we need to continue to work on to actually build the system so we have the other components so we can do a full system comparison. So this is just one part of the research. There's still more to be done, which is always the fun part and why I have a job, which is good. So that kind of gives you a view into one view of an application that you could potentially apply to, and that one thing can be applied to a variety of different problems. So next will be to actually push it further. Pretty pictures. I always like high-performance computing. So HPC, high-performance computing, and FPGAs. I'm going to show you something no one has seen yet. This is going to be so cool. You're going to be the first. There's not the level of excitement that I expected, but that's okay. So within HPC, there are a variety of different problems. And one of the things that people use are the basic linear algebra subroutines, or BLAS. And they are the core to figuring out how to do computations. And they break up into 3 different levels. There is dot product, vector times vector, matrix times vector multiplication, which is level 2, and then matrix times matrix multiplication, which is level 3. And there's a new fad that everyone does scientific computing. Obviously, the CPU did it, and that's the supercomputers. Think Cray and some other people from way back when. We won't go there, but there's that. People are looking at using embedded processors. So if you have a smartphone or an iPhone, they're basically the same thing. The processor in that smartphone they're using to try and tackle these problems. I think that's kind of crazy. I mean, it's cool. It's a different use. And then there's GPUs. So your NVIDIA or ATI card, they have CUDA or OpenCL to try and program that to do these general purpose calculations. And what we wanted to find out is, can an FPGA help? Now, a lot of people have done this in very niche areas. So we're talking oil and gas exploration. They drag these large sonar arrays across the ground or in the water, and they look at the reflections, and they try to find out where oil might be. Financial derivatives. Figuring out derivative or options trading prices. That's kind of where they've gone. And we're trying to be a little bit more generic with a BLAS. So can we do it on normal algebra or linear algebra? So inside of Microsoft, there's this project called Coconut, which basically takes matrix manipulations and you code it up in an API which allows it to create an abstract tree of the operations. So I'm adding this matrix with that matrix, or I'm multiplying this matrix by that matrix. By doing that, I can actually apply algebra to those operations and recast that problem in different light. So it's kind of like doing a proof. There's lots of ways to do a proof. I'm giving the Coconut compiler the ability to do that proof. And we wanted to see if we could do stuff with the FPGA and actually show that it's actually a useful component, then we can provide FPGA libraries that then Coconut can exploit to do particular operations. Kind of the best thing to think about is a matrix transpose. If I am doing some type of memory operation on a large matrix, CPUs are really crappy for that. But I can create a specialized engine within the FPGA to do something like that. That's just kind of a nice, simple example. I'm going to skip BLAS Level 1, just because I'm not going to show you data for that. And we're going to go directly to Level 2, which is the matrix vector multiply. So I have a matrix A times a vector X plus a vector Y, and that gives me Y prime. This is kind of the pictorial way of doing that. There are 2 different ways to do it. The first is dot product. So I'm taking a row times a vector plus a component in Y, and that gives me the first Y prime. I do that over and over again until I've gone through all the rows and gotten my entire vector Y prime. This is the one we're going to talk about, so remember that. It's not that hard to forget, hopefully. The other way is a column way, and this is using Gaxpy, which is another way to do the level 1. And I take my column, an element, all of those, and I get Y prime, and I iterate over Y prime. So I actually have to do it multiple times to actually get the actual answer. And I go through each one of these columns, and then by the time I get to this last one, it gives me the final value there. So it's just row or column major. The first one was row, this one's column. That can matter depending on what you're programming. It just depends on how you access memory. So that's a different optimization problem, but we'll just think about that. So one of the core building blocks that the FPGA gives me are these BRAMs, or block memories. They have 2 ports. I can read or write each port, each cycle. But if I just use the memory as that, I'm very limited to how I access my matrix or my vector. Right? I can only do 2 operations, and I'm trying to do a lot of things in parallel. So what we ended up doing was we banked them. So we take each one of these blocks, we put them all together, and so now I can do, in this case with 4 banks, 4 reads and or 4 writes simultaneously. So that allows me to get much higher bandwidth, and this is what the FPGA is good for. In this case, we fixed the number of banks to 4, and you can address them individually or do them in lockstep. So when I give it address 1, I take the first value from this in address 1, the first value from that in address 1, and so forth, and push it out. Or write it. It just depends on what the operation is doing. So this is going to allow me to get some parallelism out of the access to the matrix within the FPGA. Likewise, you can see how that works really well for a vector. For a matrix, basically, I just take multiple banks and interleave them together. So now I can, on a per matrix process, take a row and access that row from the first bank, access another row from the second bank, and so forth. So now I have a 2D operation in terms of how I get parallelism from my actual device, which is nice. So I have a way to access the vector. I have a way to access the matrix. It just so happens that both of those are kind of balanced, and I can do the number of operations I need to do simultaneously. I'm not blocked by one or the other component. This is the pipeline. I'm going to skip this to go to the next slide. Basically, I take that pipeline, which is doing multiplies, accumulates, and adds, and then I break up my matrix into various rows, assign a row to a pipeline, provide the vector information for the vector, and then I can actually get my output vector. So it's just a way of mapping the data and the operations to the FPGA to do all these things in parallel. So I have all these resources that I'm using. I can do 16 floating point multiplies, 16 floating point adds, and 16 floating point accumulates all in a single cycle. They're pipeline, but that's a different process. So this gives me the overall... Oh, I'm sorry. Let me turn that off. That gives me the ability to do all those operations in parallel, which is what gives me the benefit. Because when I compare this to CPU, this is running at about 100 megahertz or 200 megahertz, where my CPU is in the gigahertz range. So I have to do things in parallel to actually get speed up. Now, this is the exciting part. It's a precursor. So we did 3 different implementations of the FPGA, starting with a naive implementation. It didn't do so well. So that's that dark blue line. And as we tried to attack different issues, and these were all around the accumulator, we actually improved till we got to this version 4. So by changing the accumulator, reducing the latency, and being able to pipeline the whole process, we were able to get this consistent performance across different vector and matrix sizes. So what we got is something that's very long initially, the long vector, which is easy to do parallel stuff, to something that has very short vectors, which is very hard to do. And so that nice flat line is good. We're comparing to this black and yellow line, which is just a naive C implementation. So sitting down and saying, I want to do Gaxpy in a C program, and running it on, in this case, a quad core. So that was kind of cool. So we were able to do better in terms of performance on small data sets for this. Now, this is the really cool slide. OK, no ahs or oohs, fine. What I've done is I've taken that green line. This is the FPGA. That's the best implementation that we've done so far, and we haven't spent that much time on it. The yellow is C, the naive C. I've done the same thing in CUDA, so I'm running on a Tesla card. This is a big, powerful... OK, no one's excited. If you had a game, you'd be excited. This is an amazing card. And then MKL is the math kernel library from Intel. It's a highly optimized. Many man-years have gone into making this thing amazing. And yes, it's amazing. OK. Anyway, so that's pretty cool. And no one has seen this graph ever. Well, I have, but that's it. So this will go in a paper somewhere soon. So that's very promising from an FPGA standpoint. And I think I'll stop there. There's a lot more to do. We need to integrate the DDR controller. We need to hook it up to a PC and actually get communication between the two. But it's promising, and that's where research starts. You have an idea. It kind of looks good. You go down that path. So why Silly Putty? That's the #1 question, and I don't have much time, so I'll try to go through this. The similarities are vast. Silly Putty is a silicon-based polymer. Okay, no one's excited. B3, a silicon-based CMOS IC. It's an integrated circuit. Okay. With Silly Putty, you can mold and form it into shapes, right? And that's kind of cool. You can kind of play with it like clay. I can program the FPGA and make it into digital systems. So it's the same type of process. I use a program versus, well, in both cases I'm using my hands, but it's not so physical. I can copy old newsprint with the Silly Putty. No one's interested in that. I can duplicate designs on the FPGA. So a paper just came out where they took the Atom core, if you've heard of those, these are very small Intel cores, and they're actually able to run it on an FPGA, which that's amazing. It's at 50 megahertz compared to 1.6 gigahertz, but that's the same design. They've done it with the Pentium and other things. Okay. It has liquid and solid properties. Very exciting. I have fixed function units and arbitrary logic. Okay, not so exciting. It bounces. I can't bounce the B3, so. But I can reconfigure it on the fly. So if I'm doing one thing, I can actually reconfigure the part while it's doing something and have it do something else in the next cycle, which is kind of like bounce. Okay, never mind. Okay, I tried. That's the best comparison that I can make. In terms of limitations, if Silly Putty gets hot, it runs faster. It becomes more less viscosity. For the B3, if it gets hot, it runs slower. If it's more complex design, it's slower. If I'm using a lot of capacity of the device, it's slower. So there's limitations. If I make Silly Putty cold, it's more like a solid. Okay, no one's excited about that. If I make the B3 cold and like use liquid nitrogen, it runs faster. Okay. Gravity deforms the shape. So if I make something like a figure of George and I put it on this table, after time it will just kind of make a blob. If I don't give the FPGA power, there's no design. It just goes away. Silly Putty is flammable. I didn't know that. The downside with the FPGA is it has a long development cycle to make things work, so you may want to set it on fire. I did know that. And then it's difficult to remove from textured surfaces, hair, carpet. The FPGA has limited capacity, especially for on-chip memory. So if you want to do something that's memory intensive, that doesn't work very well. So with that, I hope I've shown you how you could use the B3 as a reconfigurable hardware computing platform. We've used the multi-core and prototyping hardware and software systems to motivate development of parallel software and tools. I've shown, hopefully, that you can do fundamental research with the Flash prototype. And with the Beehive, we're trying to get into the academic realm and use that as a pedagogical tool. And hopefully, you now see how B3 is like Silly Putty. Are there any questions? They do. You can buy it online, Toys R Us, all sorts of places. It comes in metallic form, glow in the dark, and there's all these other things that are new to me.
So is that similar to how you have like parallel processing on a graphics card, only at a different speed, or just because you're converting the way functions are being through it?
You are doing both. So inherently, the FPGA, because it's trying to be very general purpose, and you're providing the network, how things are connected together, that slows it down. So you're never, ever going to be faster than a special purpose hardware ASIC like a GPU. So GPUs are in the gigahertz now. The FPGA, the fastest it can run right now is about 500 megahertz. But you have a lot more flexibility. The GPU, if you have any control flow, any branches, if this or that, in your algorithm for the GPU, that breaks it down. Whereas the FPGA, you potentially could put that in the logic and have that part of the path and actually get speed up. If I'm doing something that is particularly targeted to the GPU, there's no way I can beat it. There's nothing that I can do on anything. So, I mean, you got to pick your tools and use them appropriately. But the FPGA for these types of applications seems promising. Other questions? Yes?
Is this, like, the overall vision of this, is this being designed to eventually become a computer in and of itself, or is it meant to be a side component?
So in the Beehive case, we've made it into a computer.
Oh.
It can do anything a computer can do, which is interesting. It's limited by how much time people have spent developing it, but you can do that. The FPGA gives me the flexibility that I can also make it as an add-on component like a graphics card or a disk or something else. So I can go both ways, which is not something I can say about everything. And probably what didn't come out of this talk is when I look at research in computer architecture, the problem that I have is I have all these processor cores running simultaneously. How do I make that next system? How do I design it? And software simulation has been used for that in the past. And it's a sequential process. So if I have the possibility of doing 10 million instructions, simulating 10 million instructions per second, if I add more cores, the number of instructions per core per second decreases linearly. It's actually worse than that. So if I have 10 cores, I can do 1 million instructions per core. If I have 100 cores, it's much, much less. So that's where we are in that regime. With the hardware, I can actually run at 100 megahertz, all the cores, and I get no slowdown from that standpoint. So I can actually investigate software. If I gave you a simulator today that's software for 100 cores and said, hey, play with the OS, you would shoot me after maybe an hour because it takes 2 weeks to boot. Right, so that's kind of the changes that we're looking at. And so you have to change the way you do research and the tools you use, and that's kind of what we're trying to demonstrate. There's a question?
I'll ask it.
Sure.
We got to go with,
Thank you very much.
Okay, thanks.